In today's lecture, we're going to do some algebra. We're going to review expressions and equations and what their differences are. And then we're going to also talk about exponential growth and also exponential decay, and then related to that, half-life. Let's get started with algebraic expressions. And so algebra basically is a way of using letters and numbers to create models for situations in the real world. And we use the letters to represent quantities that we don't know, that can take on multiple values. And our standard letter to use is X or Y. And then often we will use a letter that represents the quantity that we are talking about that's represented by that letter. So the main thing that we want to know is the difference between an equation and expression. And as we've said before, the key word or the key part of the word equation is this part, equa or equal. So an equation has an equal sign, an expression does not. And an expression is just a group of letters and numbers that are linked by operations. And then those letters are what we call variables. The numbers in front of the variables we call the coefficients. So let's take a look at an example. And in our example here, we have three expressions. In this first one, the variables are a, x, and y. The coefficient is the number part, 2. In this expression, we have two terms, and the terms are separated by this minus sign. The first term is 3ab. It has a coefficient of 3, and then it has variables a and b. The second term has a coefficient, but we don't see it. Okay, so anytime there's no number part here, you can imagine multiplying by 1 gives me the same result. So you can imagine there's an invisible 1 here. So the coefficient of this term, and we include the sign with it, this term has coefficient -1. And then the variables are the x, y, and z. And then finally, this last expression, this term has a coefficient of 5, and each term is separated by the plus signs. So coefficient of 5, coefficient of 4, coefficient of 3, coefficient of 2, and even a coefficient of 1. So we call this constant, and when a constant or a number is all by itself without a letter part, there's still a coefficient. There's just not a variable part on that one. And so notice that what breaks them up into terms is a plus sign or a minus sign. So if we take a look at another expression here, oops, that's the same one we have there. Let's find a new one. Here's a new one. Okay, so the first thing that I'm going to do when I'm identifying the terms and the coefficients is I'm going to think about where do I break this up? And remember, we break it up anytime. Come over here. Anytime that we see a minus sign or a plus sign. Okay, so we have three terms, and the first term is 4y cubed z. The second term, and actually I'm going to redo that because I didn't really draw them. We're going to draw it on this side of the either plus or minus sign. So this term is actually negative x to the 7th z to the 8th. We don't usually say positive, we just say 18x to the 4th, and the positive is implied. And then the last term is negative 5 square root 7x. So you see that the sign goes along with it. And when there's no plus or minus here, there's an implied plus. So this term is positive, a negative term, a positive term, a negative term. The coefficient of this first term is 4. That's the numeric. For the second term, the coefficient is -1. There's that invisible 1 there again. Okay, so you can imagine there being a 1 there. So this term has coefficient -1. This third term has coefficient 18. And then the last term has coefficient -5 square root 7. Okay, so every part of the numeric part gets included in the coefficient. When we have an algebraic expression and it has terms that have all identical letters and exponents in them, those are called like terms. And remember that number part in front of the term is the coefficient. That doesn't need to be the same. Just the variable part needs to be the same in order for us to have like terms. When we have like terms, we can combine them to simplify our expression. Let's see if we can identify some like terms. So here's an example. Notice here that 5xy cubed and negative 8xy cubed have exactly the same variable parts. They both have an x and they both have a y cubed. Their coefficients are different. This one has a coefficient of 5 and this one has a coefficient of negative 8. But they're still like terms because their letters and exponents are the same. In this example, 5x to the fourth and 5x cubed, those are not like terms because even though they have the same letters, they don't have the same exponents. So these are not like terms. And as I said, like terms are important because when we have like terms, we can either add or subtract those coefficients, and then we get to keep the letters and exponents, and we have a simpler expression. And a way of thinking about it is to imagine that you have 200 milligrams of ibuprofen and you have separately 50 milligrams of ibuprofen. So we know that together we have 200 plus 50 or 250 milligrams of ibuprofen. And if we wanted to give it a name, MGI, for milligrams of ibuprofen, we might represent this in this way: 200 MGI plus 50 MGI equals 250 MGI. So you can see as long as those letters match up, we can combine like terms. So here's what it looks like with algebraic expressions. I have 5xy cubed z plus another 8xy cubed z. And you can see that they both have an x, a y cubed, and a z. So those are like terms. And what that means is that I can combine them by taking their coefficients, 5 plus 8, and I end up with 13xy cubed z. Now, we might have an algebraic expression that has more than one set of like terms. So for example, in this expression, you can see that 5xy cubed z and 8xy cubed z are like terms. And then also notice that here we have an x squared y cubed z, and here we have an x squared y cubed z. So this term and this term are also like terms. We have two sets of like terms. If we would like to simplify that expression, then we can combine the two terms that have the xy cubed z, and that was 5 plus 8. So we have 13 xy cubed z. And then we can combine this one. We have negative 2 plus 9. So that gives us plus 7 x squared y cubed z. Notice these aren't like terms because the y's and the z's match up, but we've only got an x here and we have an x squared here. And then in order to have an equivalent expression, I need to get that negative 2 as well. So now this expression is equivalent to this expression. And this expression, we say, has been simplified. It's in simpler form than the original. Let's try another one. So when I do a problem like this one, what I like to do is just start with my first term, and then I like to underline it. And then I pay attention to the variable part. I have AB cubed. And then I just look, this one doesn't match. It's got an A cubed. This one has an A, but not a B cubed. This one has an AB cubed, so I'm going to underline it. This one doesn't, and this one doesn't. So these two match up. And when I combine them, their coefficients are 17 and negative 3, which gives me a total of 14. And then I write the variable part, AB cubed. And then I'm going to cross those off because I'm all done with those. And now I'm just going to look at the next one that hasn't been crossed off as I move to the right. And this part has variables a cubed b. This one doesn't match, but this one does. And so now I'm going to look at their coefficients. I've got 8 and -2. So when I combine those coefficients, I have 8 minus 2. So I have plus 6a cubed b. And now I cross those off. That leaves me with 8ab. And this one matches, doesn't it? Remember, that has the invisible 1. So I've got 8ab plus 1ab, which gives me 9ab. And now I have simplified that expression. And that's what we call it when we take a complex expression and then we write it in a more simple way. And we can't solve an expression though, right? There's nothing to solve. Solving is for equations, and we'll look at that in the next presentation. For this problem, if I want to simplify this one, what I first need to do is do a little multiplication here. So these parentheses tell me that I need to multiply, and I multiply the number parts. So 3 times -2, which gives me -6x squared. And then I have plus 8x squared. Now that I've simplified, I notice that these are like terms. They both have an x squared, which means I can combine their coefficients. -6 plus 8 gives me 2x squared. And I have now simplified. I didn't solve it. I simplified the expression. And what we call when we multiply using those parentheses is we call that distributing. And let's look at another example of representing medication to kind of help us think about what it means to distribute. So think about if you had 5 patients and each of your 5 patients needed 200 milligrams of ibuprofen and 300 milligrams of gabapentin. So we might call the milligrams of ibuprofen MGI again, like we did previously, and then we'll call the milligrams of gabapentin MGG. And so we might write that expression 200 milligrams ibuprofen plus 300 milligrams gabapentin. But notice that we can't combine them, right? You can't say, well, I have 500, they're separate things. 200 of the ibuprofen, 300 of the gabapentin. So this is as simple as this expression can be. We can't simplify that any further. And if we were considering giving this to 5 patients, we might write it like this: 5 patients times what each of them is going to get. Each of them is going to get that 200 milligrams of the ibuprofen plus the 300 of the gabapentin. So what I really need to do is I want 5 of each. 5 times 200 or 1,000 milligrams ibuprofen, and 5 times 300 or 1,500 milligrams gabapentin. So thinking algebraically, if I have an expression like this one, in the parentheses, I have the expression 200x minus 300y, and I want to multiply that by 5. Well, I can't combine the 200x and the negative 300y. But what I can do is I can multiply each of them by 5. So I have 5 times the 200x, and then minus 5 times the 300y. Notice I have to keep this sign with it. So here I have 1000x, and here I have minus 1500y. Let's look at another example here. So for this problem, if I want to simplify that expression, the very first thing that I'm going to want to do is I'm going to want to get rid of those parentheses by distributing. And that means that I have to multiply both of the terms inside the parentheses, the x and the -7, by the term outside, the -8. So I'm going to copy down my 2. And then I like to remind myself that there's a negative sign in front of the 8. So I'm not just multiplying by 8, I need to multiply by -8. So I have -8 times x, which is -8x. And then I have -8 times -7, That gives me positive 56. And then don't forget I have this 9x here as well. Now I can combine like terms. So again, starting from the left, I have a constant here, 2, and another constant here, 56. I can combine those by simply adding 2 plus 56, so 58. Cross them off because they're done. And now I have a term with an x and another term with an x. So I can combine those coefficients, -8 plus 9, which gives me plus 1x. And we normally don't write the 1, so I would write 58 plus x. And then there are a few more here. So I recommend that you give these a try. And if you're watching the video, give them a try, pause, and then come back and you can check the answers here and make sure that you got the correct answers on those. The next one that we're going to take a look at is going to be, oops, wrong one, equations. This one. These are equations. All right. So equations, we said, have an equal sign. They have terms much like expressions, and in fact, they have expressions. So you can think of an equation being two expressions with an equal sign in the middle. So one side of the equal sign has an expression, the other side has some other expression. When we have an equation, we can solve it. And to solve it means to find a value for the variable such that when we replace the variable with that value in the equation, we get a true equation. And I like to look at a couple examples of that just to make sure we understand what it means to be. Before we go about trying to solve something, it's nice to know what it means to be a solution. So let's start with a simple equation, x plus 3 equals 10. So we can say that x equals 7 is a solution because when we rewrite this equation with a 7 in place of the x, we have 7 plus 3. That equals 10. That's a true equation. So that means x equals 7 is a solution. On the other hand, if we were to try x equals 5 and we replace the x with a 5, you can see we get 5 plus 3 equals 10. That's not true. False, which means x equals 5 is not a solution. So that's what we mean, and that's how we can check whether or not something is a solution. We can always take the value, plug it into the equation by replacing the variable or the letters with that value, and see if we get a true equation. If we do, we have a solution. If not, we didn't find the solution. Now, to solve an equation, let's think about a very simple equation. We have a patient and we want to weigh them, but the patient is in a wheelchair. So what we do is we put the patient in the wheelchair on the scale. And we find that the weight of the patient in the wheelchair is 195. So we might write this equation using algebra with P representing the weight of the patient and C representing the weight of the chair. And then we would write P plus C equals 195. The patient's weight plus the weight of the chair is 195. Now, the next thing I might do is I might put the patient on an exam table or into some empty chair in the room. And then I can put the chair, the wheelchair that the patient was sitting in when we weighed the patient, onto the scale. And then I can weigh the scale. So if I did that and the scale showed me 40 pounds, then that original equation that was P plus C, person plus chair, equals 195. Well, now I know the chair weighs 40, so I can write this equation P plus 40 equals 195. And now a lot of you could probably look at that and just say, well, I subtract 40 and I know that the patient weighs 155 pounds. And that is exactly how you would do it, just using mental math. The way we do this with algebra, and I like to show it in a simple equation so that when we work with more complex equations, it starts to make sense, is I look at what operation I'm doing here. And I'm doing add 40. So what I want to do is I want to make some room in this equation. And then what I want to do is I want to do the opposite of add 40. Well, the opposite of add is subtract. So I'm going to do subtract 40. Now you can think of an equal sign as being like a scale. In order to keep the sides balanced, if I do a minus 40 here, I have to do a minus 40 here. So that's exactly how we solve this. We do the opposite of this to both sides of the equation. And then when I do plus 40 minus 40 on the left side, I'm left with P. And on the right side, I have 195 minus 40, which is 155. Okay, let's look at another example. So we have a vial that has 75 milliliters of a vaccination, and the child dose is 0.5 milliliters. And we want to know how many doses are in the vial. So let's think about that one. So the total amount in the vial should be the number of doses times the size of the dose. And that should give me the total in the vial, which is 75. And so using algebra, I might write this N times S equals 75. And then I look at, what do I know? Well, I know that the dose is 0.5, and that's this one, S. So I have N times 0.5, and we usually write the number part first. So 0.5 N equals 75. I'm running out of room here, so I'm going to rewrite the equation up here. 0.5 N equals 75. Now, what is the operation that I'm doing with the variable here? It's multiply by 0.5. And the opposite of that is going to be divide by 0.5. And I can rewrite that like this, 0.5. So when I both multiply and divide by the same number, that gives me a 1. So I end up with just N on the left side. And on the right side, I have 75 divided by 0.5, which you can do on a calculator, or perhaps you can do the mental math, and we get 150 doses. So 150 doses that are 0.5 milliliters each would give me a total vial of 75 milliliters. All right, now let's look at this one. This equation, I'm doing two things. I'm both multiplying the variable and then I'm adding something. And we kind of want to work in the, well, we actually do want to work in the reverse order. So the first thing that I do to the x is I multiply it and then I subtract. So I'm going to start with the second operation, which is subtract 2. And what's the opposite of that? Add 2. So I'm going to add 2 to both sides. Over here, I'm subtracting 2 and adding 2. And so they cancel each other out, and I'm left with 3x. And then over here, I have 22 plus 2, so I'm left with 24. A lot of times you'll also see people write these this way. Maybe you've seen it this way before. So we often don't rewrite this entire equation like we did here. We often just write underneath here, plus 2, plus 2. And then we draw a line, and then we do this addition on each side. So 3x, the minus 2 plus 2 cancels. 22 plus 2 is 24. So it doesn't matter which way you write it. They both get you to the same place. So use whichever of those methods makes the most sense to you. Now that I'm left with this expression, what am I doing to the x? I multiply by 3. And what's the opposite of multiply? Divide by 3. If I divide this side by 3 to keep it equal, I have to divide the other side by 3. And now I can simplify. So 3 over 3 is 1. So I just have x on the left side. And 24 divided by 3 is 8. So x equals 8 is the solution to this equation. And we can check it by rewriting the equation. And where that x is, we're going to put an 8. And then we're going to check. 3 times 8 is 24. 24 minus 2 is 22. So it checks out. X equals 8 is a good solution. Okay, now we've made it a little bit more complicated. So you can see that we're adding and then we're multiplying. So when we have a problem like this one, there's a couple different ways that you can do it. Often we distribute, like we were talking about a little bit earlier when we were looking at expressions. So we can start by distributing this. Remember, to distribute this, I have to multiply both terms in the parentheses by -3. So -3 times x, and then -3 times +2, so -6. And now that I've done that, I look at my operations and I'm first multiplying x by -3, and then I'm subtracting 6. So I want to start with the last operation, which was subtract 6. And I'm going to do the opposite, add 6. And I'm going to write it up and down. So I'm going to add 6 to this side, add 6 to this side. When I add here, the -6, +6 cancel, so I'm left with -3x. On the right side of my equation, I have 24 plus 6. And now what am I doing to my variable? I'm multiplying by -3. So I'm going to do the opposite, which is divide by -3. And I can write that as over -3 because the fraction bar means division. Here I've got -3 over -3. They cancel and leave me with just x on the left side. On the right side, I have 30 divided by -3, which gives me -10. Right, that's a similar problem. Let's try a little bit more complicated one. So we've got a lot more going on here. We're going to start with distributing. So whenever you've got parentheses, that's always a good place to start. I'm going to recopy down everything else. 8x. The coefficient here is 4, so I have 4 times 2x. That's another 8x. And I have 4 times -7. So -28. I'm going to copy everything else. -3 equals 6 plus 3x. And now I'm going to collect like terms. On the left side, I have 8x and 8x. So I can add those coefficients to get 16x. Cross them off because I'm done. And then I have -28 minus 3. So a -28 and a -3 gives me a -31. I can't do anything to this side because they are not like terms. And now notice that I have x's on both sides. Whenever this happens, I want to get the x's all on one side. There's a couple different ways to do this. Some people like to have all the x's on the left side. Some people like to keep the x's positive. In this case, we can take care of both at the same time, right? We can get rid of the 3x here. Well, how do I get rid of a 3x? The opposite of adding 3x is subtracting 3x. And I usually like to write it under the like term so I know what I'm doing. And then when I subtract that from both sides, I have 16x minus 3x. So that's 13x. And I still have the minus 31 here. On the right side now, I just have 6 because these two cancel. Now I'm back to something that looks more like the simple ones we did at the beginning. And the second operation is this minus 31. So I'm going to do the opposite of subtract 31, which is to add 31 to both sides. On the left side now, I'm just left with 13x. That negative and positive 31 cancels. On the right side, I have 6 plus 31, which is 37. And then now my last step is going to be divide by 13. So I have x equals 37 over 13. Now, when we have an equation like this one that has fractions, you can work with the fractions and do all of the things we've been talking about, but it's usually a lot simpler to eliminate the fractions. And we do this by finding the least common denominator of all the denominators. So we find the least common denominator, and then we multiply every term on both sides by the LCD. And what that's going to do is it's going to, fractions, numerators and denominators are going to cancel, and I'm going to be left with no more denominators. So the least common denominator of 5, 8, and 40 is going to be the least common multiple of those. So I look at this and I know that 5 times 8 is 40. So that tells me that that's going to be my least common multiple. So I'm going to multiply everything by 40, okay? Times 40 times 40. So on the left side here, I have to distribute. I have 40, and if it helps you, write it as 40 over 1 times 2/5 x. Then I have to multiply 40 by positive 1/8. So plus 40 over 1 times 1/8. And over here, I have it's equal to 3 over 40 times 40 over 1. And now we can cancel some things, right? So remember, anytime I have a factor that divides into both a numerator and a denominator that are being multiplied in fractions, I can simplify. So I can divide 5 into 5, it goes once, and 5 into 40, it goes 8 times. And what I'm left with for this term is 8 times 2 times x, 16x. My denominator is just 1 times 1. So I don't need to write it anymore. I can simplify this one too. So 8 goes into 8 once, and 8 goes into 45 times. So I'm left with plus 5 times 1, which is 5, and a denominator again of 1. And then finally for this one, the 40 in the numerator cancels with the 40 in the denominator, and I'm left with 3 over 1, which is just 3. And now I can proceed as we've done before. So the first thing I want to do is the opposite of add 5. So subtract 5. On the left side, I have 16x. And on the right side, I have 3 minus 5, which is negative 2. And then finally, the opposite of multiply by 16 is divide by 16. So I have x is negative 2/16, which I can simplify to negative 1/8. Here's a few more that you can try. So at this point, if you're watching along on the video, I recommend that you pause the video, give these a try, and then when you start the video up again, you can check your answers here. And then the next thing we're going to be looking at is exponential growth and decay. And we'll start with an example. We have a highly contagious virus. It's passed from person to person, and it's estimated that every person who has the virus will infect 2 others before they get well. So the question is, how does that impact the spread of the virus? So let's assume we start with 1 person. Okay. So we have our random person, Teddy, who has caught the virus. And we know that Teddy's going to pass it on to 2 people. And then we know what's going to happen next. Well, each of those 2 people is going to pass it on to 2 more people. So now we have 1, 2, 3, 4, 5, 6, 7 people sick, and it's only round 3. Now each of these 4 people are going to infect 2 more people. Now we have 15 sick people. Now when each of these people infect, now we're up to 31 and then 59, and you can see that this is starting to grow really quickly. We're not just going 2, 4, 6, 8, 10, right? We went 3, 7, 15, 31, 50, 59. So it's growing exponentially. And the next time we would be up to 64 people. And by the 12th iteration, we now have 2,006 sick people. If we were just doubling, or if we were just adding two sick people each time in 12th iteration, we'd only have 24 sick people. So this happens really quickly when we have exponential growth. And we use this equation to model it. So P, the little p, or sorry, the large P by itself here represents the starting population. So in this example, we started with 1 sick person. R is the growth rate, okay? And then T is the number of periods that the population is growing over. And then what we end up with here, population, is what's the size of the population after T time periods. And we can measure that in days or years or hours. It really depends on how quickly, if a population is growing over minutes, then we would measure it in minutes. If it's a population that's growing a little bit more slowly over days, then we would measure time in days. We just want to make sure that all of the times we measure. So if our growth rate is in days, then the time periods that we enter have to be in days. Let's look at an example. We have a bacteria colony, and it grows by 45% every hour. We start off with 1,000 of the bacteria on a doorknob. A nurse comes along, touches the doorknob. She picks up 200 of them. 150 of those are transferred to a patient. So in terms of this spread, what does this mean? So remember, we had that equation. The population after a period of time t is equal to the initial size of the population, which was 150 in this case, times 1 plus the growth rate, and the growth rate was 0.45, so we can write 1.45. Raised to the t power. And our growth rate was in hours, so t represents the number of hours. So if I want to know what this population looks like after 3 hours, I'm just going to replace this with a 3. And that's something that we can easily do with either a calculator or, let's see here. Let's go over to Desmos. Oops. Lost our place here. Okay, so here's our equation, okay? And the growth rate is in hours. So if I want to know what this looks like after 3 hours in Desmos, I can do this. Oops, 1.45. And then to the third. So after 3 hours, we would have a population of 457. Let's see what that would look like after 8 hours. I'm just going to copy this. And I'm going to change that to an 8 up here so that we can compare. Whoops. Yep. Okay, so after 3 hours, we had 457, and after 8 hours, we have almost 3,000. So you can see exponential growth happens very, very quickly. We can also talk about exponential decay. That is what we call when a population is decreasing. So say we have a bacteria that we're treating with an antibiotic. Hopefully the antibiotic's working and the population of bacteria is decreasing. And if we have an antibiotic that causes the population to decline 80% per day, then we're going to use this very similar formula. Notice the only difference is the sign here. Okay, so with population growth, we're adding the rate each time period. With population decay, we're subtracting it. So if we have a decay rate of 80% per day, then we would put 80 here. And the equation would look like this. The population is P times 1 minus 0.80 to the T. And then we can simplify that. 1 minus 0.80 is 0.20. So I could see what that population would look like. Let's imagine that we started with this population of about 3,000. And it's decaying by 80%. So 1 minus 0.8. And then in Desmos, I can also do this. Okay, so I can put 3,000.2 to the T and add this little slider. And then I can see that after, what was our time period here? This was per day. So after 1 day, we're down to 600. When T equals 1, we're down to 600. And then I can slide it over here to 2 days. We're down to 120. 3 days, we're down to 24. 4 days, we're down to 4.8. And 5 days, we're down to 0.96. Let's look at another example here. We have an initial population this time of 1,500,000 with an 80% per day decay rate. So let's change this, add in some zeros here. Actually, I'm going to change this one here. Let's get rid of these. And we're going to change this to 1.5 million. Okay. What did I do that it didn't like? Let's do. Okay, I think it wants me to get rid of that first. Here we go. Ugh, why does it not want to give me that slider? Now let's try starting again. There we go. Like that. Okay. So if we start with a population of 1.5 million, then after 1 day, we're down to 300,000. That's a nice decrease. After 3 days, we're down to 12,000. Also really good decrease considering we started at 1,500. But notice this kind of shows you the importance of finishing a course of antibiotics, right? Because at this point, the patient went from 1.5 million to only 12,000. So they're going to start feeling better, but the bacteria is not gone. So they got to keep taking this, right? Let's see how long it takes till we get I'm not an expert in medicine, so I don't know how much you want to have for it to be considered gone, but you can see it takes until day 9, was it? We don't get to less than 1 until about day 9. And then we have one more topic which is related, and that is half-life. And one of the things that we measure with half-life is medications, how long it takes for a medication to leave a patient's system. And the equation for half-life is that the initial dose times 1/2, with its half-life, and then the T represents elapsed time. T to the 1/2 represents the half-life, how long it takes for half of the medication to leave the patient's system. And then the amount tells me how much is left at the end of that time period. Let's look at an example of Atenolol, a beta blocker. It has a half-life of 6 hours. So if someone takes a 75 milligram dose, 6 hours later, they still have 37.5 milligrams in their system. And then 12 hours later, they still have half of that. So each 6 hours, half of it is leaving their system. So the equation for this one would look like initial dose is 75, and then here the half-life is 6. So if I wanted to put this one into Desmos, I would do 75 times 0.5 to the, and I'm going to put parentheses here, T over 6. And again, I'm going to add that slider. And so you can see, we said after, oh, we were looking at something else. So after 6 hours, that's 1 half-life, right? We would be left with half of the medication, 37.5. And you can also kind of update this, like if I want this slider to go bigger. So I don't really need it to be negative because I'm talking about over time. Time's only going to be positive. I might want to look at up to 10 half-lives. Oops. Since a half-life is 6 hours, I might change the step to 60. And I'm sorry, the max to 60. And then I might step through by 6s since, and then why is it not showing me that? There we go. You have to click on the expression to get back to your slider. So here I can see after 13, still have 16. After 13 hours, I still have 16 milligrams. About 24 hours, I'm down to 4 milligrams in my system still. Okay, we did most of those. And then some of these questions will ask you something like this: how much of the medication is in their system at another time? So if you have and let's actually just look at these. So we have the equation there. If the patient takes the dose at 8 a.m., how much is still in their system at 2 p.m.? So from 8 a.m. to noon would be 4 hours. From noon to 2 would be 2 more hours. So that would be a total of 6 hours. So that's that half-life. So we would move this over to, oh, I started it at, I see what I did. I started it at 1. Let's start it at 0 and step through by 6. That'll work better. And I'd click on here to get it to go back. There we go. Okay, I like that better. So we can see after 6 hours, we have 37.5, 12 hours, 18.75, 24 hours, 4.6875, and so forth. So to answer this question, some of these other questions after at 8 p.m., if we took it at 8 a.m., that would be 12 hours. So that would be this one. Right, I think that's pretty much all we had for that. This is a related question. I had pulled up some questions from last time's homework. So this one is very similar to what we were doing here. One of the ones that a lot of students found really challenging, let me go to the next page, was this one. That we have a virus with an infection rate of 60% per week. And when it's discovered, 100 people are affected. So remember, for that one, the equation is population is initial population, in this case 100, times 1 plus rate, which is 60 to the t. So I might write that in here, 100 times 1.6 to the t. And the question is, and I'm going to click there to add that slider. The question is about how many weeks will it take for 115,000 people to become infected? And when this was given last semester, there were multiple choices. So we are trying to figure out what the value of t is that gives us a value of 115,000. So we don't have the tools from this class to solve it directly. We would have to use logarithms to solve it directly. But with Desmos, this is pretty easy to solve because all I really need to do is manipulate my slider until I end up with a value of 115,000 here. And again, I don't need these negative values, so I'm going to click on here. Nope, I got to click, there we go, click on that number. And then I'm going to go from 0 to 20. And I'm going to step through by, I'm going to have it step by 1. And then I'm going to click back over here again. And now I've got my little slider. And so I can see that after 4 weeks, we have 655 people that are infected. And after 8 weeks, we have 4,294. So for a question like this one, I can just kind of scroll through here until I get close to 150,000. Since I'm given multiple choices, I might want to start with one of the middle numbers, like say 14. Okay, and that gives me 72,000, so not enough. So I go up to 15. And there we go, 115,000 and some change. Okay. The other way to solve this is to just enter some values for t here and see what happens if you don't like using the slider. So since we were giving the multiple choices, I'm just going to copy this here. So I could just start putting in some values and see, does 13 work? Nope, too small. 14, too small. 15, there it is. Okay. So even though we can't solve it directly, we're not asked to give the exact number of weeks. And so we can get close by just plugging in some values and playing around with it. And that's what we have for today. So please do reach out if you have questions about really anything at all. Have a great week.